Good morning, everyone. This is the Don Chappelle Natural Philosophy Society Science Chat. I am your host, Franklin Hu, and we're here to discuss all things science. So here today we have Dennis Allen and Bob Gray, Alistair, and Ian Cohen here with us today. Morning, folks. So Dennis was telling me that he just published an update to his book. So why don't you tell us what you did there?
Well, I had to add 2 appendices. I mentioned them last time, I think. And I got my son Pat to put them into a Word document because I don't have Microsoft Word on my home computer. I used to go to the library and take care of it there, my local public library. So the latest version, the 4th edition, is now on Amazon for about $5, I think. I forget exactly. And it's a paperback, and it can be freely downloaded from researchgate.com and also academia.edu.
All right. Well, let me see here. Let's see if we can look that up. If I get in the ResearchGate here. So I would look for Dennis Allen, I would presume.
Dennis Allen Jr., yeah.
Of course, I can't share this with you. Let's see here. Dennis, there's actually a couple Dennis Allens here. You must be Dennis P. Allen.
Yes.
And so if we take a look at what you've got here, you can find what your featured research. Is this the Foundations of Gaussian Mechanics, or what's the name of it?
4th edition, yeah, 4th edition.
And then you have Appendix 1 and Appendix 2.
But that's to the 3rd edition. The 4th edition includes those appendices as part of the book.
So was that the basic change you added?
One of the things I added was that Gaussian works with the complex numbers. His machines are basically 2-dimensional in that he talks about something rotating in a circle, more or less, where each quarter turn it either accelerates or decelerates or something, so that he gets what he calls frequency modulation. He's an electrical engineer, and frequency modulation is very important in electrical engineering. And he generalizes that to mechanics. And but this only works in 2 dimensions, really. And that's why you can get by. The complex numbers are a 2-dimensional vector space over the real numbers. 2 dimensions are the real part and the imaginary part. And he likes the fact, as all electrical engineers do, because it's tied in closely with alternating current circuit theory. He likes the fact you can multiply 2 complex numbers. In other words, 2 2-dimensional vectors over the reals. You can multiply them and get another complex number, which makes sense as far as alternating current circuit theory is concerned. It's not just some product that has nothing to do with anything. It fits like hand in glove in alternating current circuit theory, and he's extended that to mechanics. But he can't, for the Boeing inertial propulsion, you have 2 rotors spinning in opposite directions but with the same angular velocity, and then you move the axes a little bit here and there relative to each other to get inertial propulsion. But this is a 3-dimensional situation because, when you move the axes, that's the 3rd dimension. So his mechanics needs, in my opinion, to be generalized to take to hopefully explain also the Boeing inertial propulsion technology, which is multi-million-dollar, of course. And how would he do this, though? Well, there's 2 ways. One is that the quaternions are basically three-dimensional. They also have a scalar, but they basically are three vectors with a scalar. And they're not a field, though, like the reals and the complexes. They're a skew field, which means that the multiplication need not be commutative. XY need not equal YX. So there are only four, well, I guess there's only, there's the real numbers, the complex numbers, and then the quaternions, which are a skew field, not a field like the other two. And this has application to electrical engineering too, because a guy by the name of Eric Dollard, who's out on the out west, and they call him the new Tesla because he's apparently replicated Tesla's magnifying transmitter and got it to work. Anyway, he's published a 2-volume work entitled Versors. When he published it, someone wrote him and said, this is just basically quaternions. He had never known that. So, you know, it's like they used to say, there's no stopping an idea whose time has come. And it seems the time for the quaternions has come. And so it may be that Gushki, if he moved from the complex numbers to the quaternions, could then mathematize his theory in 3 dimensions instead of just in 2 with the complex numbers. And the other thing is that his book on two-dimensional mechanics quotes from the University of Texas on uniform circular motion, which is just basically the Serre-Frenet differential geometry, differential curve theory, but with the torsion set equal to 0. The torsion, if you think of a particle moving in a spring-like trajectory, the torsion would be how fast you move in the upward along the axes as you travel along the spring-like curve. Can't think of a sort of like a corkscrew. So if you take Serre-Frenet formula, Serre-Frenet differential curve theory, and you restrict the torsion to be 0, so you can only go around in a circle. You can't go upwards as well as go around in a circle. You get what he has in his book on from the University of Texas. And I think that may also be a way that he can generalize his mechanics to 3 dimensions and explain the BOEING inertial propulsion technology. I strongly suspect that since the BOEING people are engineers rather than mathematicians or physicists, that what they do to predict how their inertial propulsion technology will work in outer space in their satellites, what they do is they cherry pick Newtonian mechanics, I believe. I don't think they have a theory that is hard and fast like Newtonian mechanics, which, however, is wrong in the case of inertial propulsion. So this might be of interest to them too, but I've sent copies of my book to various people, and I haven't gotten a lot of good feedback.
All right. Well, that's. Oh, by the way, so you were looking for the videos for the inertial propulsion. Did you find those?
Columbia. No, it's been taken down. Someone found out about that, and they did what they always do. They just take them down. You know, no explanation, nothing. Just they're gone. You know.
Well, there was the inertial propulsion website that had looked like some of the actual.
Yeah, I did, but not the Columbia one, as far as I could tell.
Uh-huh.
I want to thank you for sending me that, but unfortunately, whoever's doing this sort of thing knows what they're doing.
But now you're claiming that this technology is already in use in satellites built by Boeing, right?
Yes, that's what Mike Gamble said in his 2015 Integrity Research Institute talk at the Tesla Tech conference of that year. He also gave a Tesla Tech talk, but that was just had nothing to. There was a disclaimer saying that this includes nothing that we're doing at Boeing. It's just my thoughts, basically.
Well, then how do we know that Boeing actually using these things?
You can get a copy by calling Tesla Tech, and it's about $30 with shipping and handling, although it may be marked down now since it's 2015.
I mean, if I Google Boeing using inertial propulsion, if I can. It looks like someone has searched for this before, but I don't see anything directly about that.
Well, you see, when Mike Gamble gave that talk, it took him a year to get permission from the Boeing people to call it a Boeing approved talk, and he had a number on the slides. If anyone's interested, I do have the slides, the PowerPoint slides to that talk. And so after he gave the talk, I think they had second thoughts because people criticized him, no doubt, because that's contrary to Newtonian mechanics, and we know Newtonian mechanics is right. So since Boeing is interested in making money, not advancing science, they seem to have pulled their head in and like a turtle, and they're now back to saying, well, no, control motion gyros, which is the name of the technology, the official Boeing name, only really rotates the satellite. That's all it does. They're back to saying that again. Although, as I say in the Boeing approved talk, Mike directly contradicted that. And you can get a copy from Tesla Tech for about $30 if you were interested. Or you can email me and I'll send you a copy of the PowerPoint slides to that talk, which contains a lot of information on their IP technology. But if I understand him correctly, they have to get the right answer, they have to cherry pick Newtonian mechanics, because if they use the complete Newtonian analysis, since momentum is conserved in any complete Newtonian analysis, you wouldn't get any effect, but that they use it in their satellites to get an effect.
Well, so, you know, if you can show those slides on your screen, you can share those with us right now if you'd like.
Well, I don't know how to do that. How do I, if you walk me through it, I can send them to you and then you can...
Well, unfortunately, I can't show anything on my screen. So I'm still having this technical problem. But can you view the slides on your machine?
I don't think so. I'm not computer savvy enough for that.
No, you can't find the file and click on it, and maybe you have the program.
Well, all right, I'll click here and see what happens, but I'm afraid it'll knock me out of the conference.
Okay, if it does, then just make sure to come right back, right?
All right, okay.
Let's see whether you can do that, because you can share anything that's on your computer.
Okay, now I should send them to you, right? Or how are we going to do this?
Well, you can send it to me, but I can't show it.
Okay, well, what do I do then? You walk me through it. I've got...
maybe I can get them up on my screen.
Well, do you have it on your screen, Dennis?
No, I have to go into Gmail, and then
so James, you're saying that you might be able to get it and show it?
Yeah, I can send it to James. I
and by the way,
I can send it.
Well, I already got it from you, Dennis.
Oh, All right.
I already got it for you. I could try to put that up. I have to start PowerPoint and put that up on my screen. I did put up in the chat the URL for my BitChute channel, which the latest video is the one on inertial propulsion, which I think we talked about ago. And that video has been the most uh, widely viewed video. And in fact, in terms of the amount of time that it's been up, which has been about a week or so, um, over 130 views, I think, as of now, which is a huge amount for a technical video in such a short time. I sent to Twitter to @Boeing Space, which is the part of Boeing that does this activity that Dennis is talking about, and telling them about this video, providing the link, and saying, "You're welcome. This is the mechanism of inertial propulsion. You're welcome." So
Well,
perhaps some of the people who have watched my video on inertial propulsion mechanism have, in fact, been from Boeing. Now, I can, let's see, I can try to find in PowerPoint this presentation that Dennis is talking about, and maybe share my screen. This might be a little bit awkward, but since I can do it, why not? Let's see. File.
Yeah,
let's see.
So
you all can proceed talking. I'll see if I can get this up on my screen. Okay, I got
a question for you, Roger. It says, "Do you think that Einstein is the greatest genius of all time?" How about it, Roger? Actually, I think Einstein is like the greatest dissident of all time, right? Because then he actually succeeded in completely changing everybody's mind. Right? I'm not quite sure how that happened, but certainly he was the most successful, basically non-mainstream. I mean, he wasn't even a legitimate scientist. He was a hacker like us. And talking with his friends in little groups like this, and then somehow Max Planck got a hold of it, and somehow he became famous.
I don't know whether that. Can you hear me? So,
Yeah, we can hear you, Roger. Go ahead. What do you think?
Yeah, I don't know where that question is coming from, because normally I'm talking about the genius of Boscovich, and I'm not really talking about the genius of Einstein. So I don't know what that's supposed to mean. Is Einstein the greatest genius? Usually in the physics mainstream, they say Einstein is the greatest, don't they?
Yeah, mainstream says that, but I don't know why Robert Kidd is asking you particularly about your opinion.
Yeah.
Also, here's the link to James's website here, so you can. On the very top of that website is his latest video about inertial propulsion.
Oh, okay. I can attempt to put this Boeing GYRO by Mike Gamble PowerPoint presentation on the screen whenever you want. Just tell me when you want to advance the slide, because I assume I'm not doing the talking. I assume that Dennis is doing the talking here. Do you want me to try to put this up on the screen now?
So you have to share screen. I don't see the screen yet.
Here we go. I'm going to try to share my screen, so bye-bye. You won't see me share screen, and then it says share screen. I click there, share.
There we go.
Then James Keen's screen.
Good.
Yeah. Oh, okay. Can you see the screen? Now I'm
Let's see, we're
going
waiting for it. Okay, there we go. We can see your
go to
screen
the
now.
PowerPoint slideshow, start the show. And there it is. Now, I'm not going to do the talking. I'm just putting this up as a convenience for Dr. Allen to, or whoever else wants to discuss this. Just tell me next slide, okay?
Notice
Okay,
that the Boeing approval number is right under the title. 7th International Conference on Future Energy, Boeing number 15-00051-EOT. And notice the date under Michael's name is 2014. That's because it took him a year to push it through the Boeing bureaucracy, and he basically it was basically a stealth type deal. He didn't say any more than he had to about the possibility that Boeing would be heavily criticized for making an announcement like this by the powers that be in physics, especially mechanics. So the date is 2014, but the talk is 2015.
Well, the initial title here seems rather innocuous, which is the Control Moment Gyro.
That's not the title. That just is the conference. Go to the next slide.
Next slide, yes.
You have it. Say something. I don't hear anybody. This is the next slide.
Yeah, we got it.
In my book, there's a short presentation which was written actually by Mike Gamble, and at the end of the presentation, that's in my book, I put in brackets that this is, from Mike Gamble or some words to that effect. So if you want to know the history beyond what's here in the introduction, you can look in my book for it.
Okay, well, let's go to the
next slide.
It's interesting that the research was destroyed by the earthquake.
Yeah, it's an act of God that this came out.
This is the next slide.
So that's the Space Center. That's close to where I live. My dad used to work there.
Oh, is that right?
In Kent, Boeing. Yeah, next slides. We got a picture of Mount Rainier back there.
Okay. Next slide.
Gyro operating principles. Next.
Yep.
Now I was going to explain how it works. It's called scissoring, like scissors that you cut things with. They have two rotors spinning in opposite directions at the same angular velocity, and they move the axes relative to each other in 3 dimensions, not 2 as in Gushke's mechanics. And so Gushke can't explain this.
Well, so far, nothing controversial here. So next.
Now, it's pretty straightforward, their thinking. That's why I believe they're actually cherry-picking Newtonian mechanics rather than having their own theory that makes sense everywhere,
And if I might add, thanks to Dr. Allen, he sent this PowerPoint to me. And in this slide, for example, I don't see anything about actually what the mechanism of exactly how it operates is. In other words, where... Yes, go ahead.
Go to the next slide. That'll that should tell the story on that. Now here you got 2 rotors spinning in opposite directions. Now you can move the axes; they're parallel right now, although the Angular velocity vectors are anti-parallel, of course, since they spin in opposite directions. But if you move the axes so they're not quite parallel anymore, depending on how you move them, you get inertial propulsion.
Okay, that's the phenomena, but not an explanation of how it works, what the underlying physical mechanism is.
In the last slide, it showed that if you push if you move the axes to the side, it actually moves up, not to the side. That's the idea.
Well, again, that's the phenomena, not the explanation of why the phenomena produces the result, in my opinion.
Well, they just go by gyroscopic theory, but without doing a complete analysis, which would inevitably show that there was no effect when there is. So if you take the spin axis and you rotate it a little bit, the thing doesn't move in the direction of you push it a little bit, the thing doesn't move in the direction of pushing, but rather up or down if the pushing is sideways. So the output is at right angles to the input.
Now, is this picture
So again, what Dennis?
That's what I want to know.
So again, what Dennis Allen is saying is the phenomena of it, much like was seen in the Lathwaite video, and this is just the phenomena. It doesn't explain how this phenomena produces the effects that one can observe, in my opinion.
Well, yeah, they don't have.
We don't care. I want to see that the phenomenon actually occurs. So, like in this picture, it shows like two blue arrows. They seem to be heading in the same direction.
No, they're opposite directed because they're the angular velocity vectors. They're oppositely directed since they're spinning in opposite directions. They're anti-parallel, the two vectors.
Yeah, but is this going to show that this box will just like try and move in one direction?
Well, go to the next slide. I think it's in the next slide.
Okay, next slide. In this case, just the observation of the phenomenon itself is significant. I mean, regardless of how it works or regardless of if there's any explanation for it, it was quite significant to have inertial propulsion.
See, here they explain in terms of this input-output diagram, which was our first slide on the actual works. They explain what they do, but of course, this doesn't completely explain it because it's cherry-picking Newtonian mechanics. If they did a complete analysis, then there would be no effect, but there is an effect. So Guschke's mechanics for two-dimensional, this is three-dimensional, unfortunately, or fortunately maybe, but Guschke, if you have a two-dimensional setup, he can explain, based on his mechanics, just why what happens. And that's, I think, what James Keen is talking about. But in three dimensions, Guschke can't handle it because his mechanics is two-dimensional at present.
Well, looking at this graph, it looks like the top part is showing how fast they are spinning the gyros. So they go from slow, and then I don't know why they're showing it going down and saying fast, and then going up and then down. It looks like they're changing the gyroscope speed, and on the bottom they're showing the force. So during this slow part of it, looks like there is a downward force, and then during this fast part, there's a spike with a large upward force, and then they have to repeat backwards and go down. So I think what he's showing there as the average is like what the average force would be, which is still net up. So I guess that's the inertial propulsion.
I don't think so. they're moving the axes relative to each other slowly or rapidly moving them. Because the input-output diagram is that if you move to the right, the thing either goes up or down. I think up. Of course, it depends on which way it's spinning too. So you can either move the axes fast, as like a scissors, you know, where the blades approach being parallel as you close the scissors. So if they move slowly, the effect is less, and if you move fast, if they move the axes relative to each other fast, then you get a much bigger effect from gyro theory as cherry-picked by them.
So it's like you put some gyroscopes on a scissor, and you like slowly open the scissor, and then you shut it very quickly. Maybe that's what he's showing here, right? And when you
I think that's where it comes down to it. I think so. That's right, Franklin.
So when you do that, then you appear to get this net upward force, even though there is this, you know, negative downward force as you do this, because you can always get some displacement, but you always have to return all of the displacement that you got before, right? Like if you're in space, you can like you can move your feet towards your hands, and you know that does move you, but doesn't move your center of gravity. Is what it doesn't move. Does not move your center of mass. But this would be suggesting that the center of mass would actually move, right? It was in a say a weightless environment.
In the satellite.
Should average still go up, I guess, right?
Yeah.
Okay, well that's interesting. So that's the direct evidence of this kind of inertial propulsion, but the mechanism seems very simple. I mean, as opposed to what we had seen before. It's just
now Tesla Tech, as Bill Lucas tells me, Tesla or SpaceX, I mean, is got a spaceship that's going to lift off without any rockets. They're partially under construction, and they may use a more sophisticated cherry picking technique than this. I don't know. No one seems to know. Except them.
I'm not quite sure what you're talking about, cherry picking. I mean, that's usually an experimental.
If you calculate every single force and add everything up correctly vectorially, because Newtonian mechanics has conservation of momentum and angular, separate conservation of momentum and angular momentum in an isolated system, you can't move the center of mass. But they use them in their satellites to move the center of mass to a higher orbit. So there has to be something wrong with Newtonian mechanics. Still, if you ignore certain parts and choose other parts correctly, then you do get what you've got here on the screen. It's like quantum mechanics. Feynman made the point before he died that there are all these infinities that come into their equations. And they have to know it's more of an art than a science how to get rid of them and get the right answer so you can build nuclear weapons and stuff like that. But, you know, they know what they're doing, and so their bombs work. You know, their hydrogen bombs blow everything out. But they to do that, to get so they can get these bombs to go, they have to know how to cherry pick quantum mechanics and what infinities to throw away and what not and so on. It's like that's about the best explanation I can give.
You notice in this diagram here where I'm highlighting the upslope of the force curve here with the red cursor is similar to the data I presented 2 weeks ago on inertial propulsion and how it takes a little time to develop the full effect of the translation due to the initial rotation injected into the system. So I just wanted to point that point of agreement out. for what it's worth. Shall we go to the next slide?
Yeah, next slide.
Yeah.
Different types of gyroscopes is all it says. Next slide after that.
Yep, next.
Small gyro, first type.
Yeah, it's
They've got some
he has a
figure
lot
eight
of equipment
bands.
slides. The only reason he could give these pictures is that all this stuff was destroyed in the earthquake. And so according to the obscure Boeing rules, that meant that it wasn't kept secret for 100 years. They could release it immediately because it was in the junk pile. So in other words, if the earthquake hadn't happened, there would none of this would ever have gotten out.
I don't understand what.
But I did.
Why was it allowed to be released because of the earthquake?
Yeah, because Boeing has in their rules and regulations that if a laboratory that was no longer in existence had some photographs associated with it, then you could publish the photographs. You could get Boeing's permission to publish them. Now, the people that wrote this obscure rule had no idea that an earthquake was going to occur and that the building would be destroyed, so it would be no longer in existence. They expected that it'd be 2090 maybe before it could be released, and then it would be old hat, of course.
But I suspect that after the earthquake, devices such as this were built in other buildings because, after all, as Dennis Allen has alleged, they're using these devices in Boeing satellites presently, the low-altitude ones, particularly.
Well, I think they claim now that they're using electromagnetic inertial propulsion because that's not, no one comes down on them hard because of that. Since Newton's third law, which you need to prove separate conservation of angular and linear momentum in an isolated system, is not embraced by relativistic electrodynamics. So it's all right to have inertial propulsion if it's an electromagnetic phenomenon, but it's not all right if it's a mechanical phenomenon. So what they seem to be doing is saying that, we're using inertial propulsion, but it's electromagnetic, and so that's all right. Don't criticize us anymore.
Well, from what I was browsing around briefly, they'll say that they use ion engines, which is mostly a fully electrical type of propulsion, although even that still requires the use of some propellant. They still have to spit out a gas, or somehow collect it and do that.
Well, there's a small group in NASA headed by a guy by the name of Brady. I don't know his first name, unfortunately, but he's in Texas. He has a small group, and they've designed and built an EM propulsion device, which there's no ions or anything. The only thing that goes out is electromagnetic radiation, and it goes by radiation pressure, I guess. And so the big problem that they found, though, is that when they test it, they do get a small thrust, but since they can run it 24 hours a day in space, it mounts up after a while. But the problem they're having is that when you switch the drive off, it doesn't stop pushing. They have no idea, I guess, why this is. Apparently what the problem is that relativistic electrodynamics is wrong, and so you can't always get the right answer by using it. This guy is in Texas, and he works for NASA, NASA, Mr. Brady.
Well, that might be just, the criticisms of these EM drives is that the force that they're measuring, which is rather small, is due to other effects, like some kind of electrostatic effect. And that's why when they do these control experiments, you turn off the power source to the drive, but it still keeps on going, which indicates that to the critic that the force you were observing wasn't due to your EM drive. It's due to something else in your experimental setup.
Well, I guess NASA has tested it, and it worked according to their specs. But the problem they're having, as I say, is that when you switch the thing off, it continues operating.
Yes, and how can that be?
Yeah, I know it. It isn't possible if relativistic electrodynamics is correct. But there's an article by Achilles, which I brought on an earlier meeting, that shows that there's a magnetic effect that when a permanent magnet is rotated, a cylindrical permanent magnet is rotated about its axis, then the magnetic lines of force also rotate. Now, Faraday said, no, that's not right, because the sun rotates, but its rays do not. And Steinmetz said, well, maybe it's true and maybe it's not, but who cares? Because either way, you get the same result. He was working with unipolar generators. But Wesley has pointed out that, and also Achilles has explained an experiment done by another guy whose name I don't recall, and according to that, relativistic electrodynamics is wrong, because when a magnetic field, permanent magnet rotates, so its lines of force also rotate. So, and that causes different effects than in relativistic electrodynamics, where that they don't consider the possibility of magnetic lines of force rotating or not. They don't go into that.
Yes, I think the contention that the lines of force do not rotate when the magnet is rotated was introduced to try to explain unipolar induction, that the moving disk was cutting its own lines of force and therefore generating an EMF. But I think the series of experiments that are given by Kelly and others would seem to indicate, in my humble view anyway, what you've said, I think, Dennis, that the lines of force do actually rotate with the magnet.
Yes, I think you're right.
All right, let's get back to the slideshow here. So what's the next slide?
Oh,
That's
it's another.
Second type. You can hardly see anything here.
Oh, it's you're not getting into the resolution. It's because the photograph is you're not seeing what's all that's there. I don't think. Maybe we gotta go to the next slide. You know,
Yeah,
here,
I can see that. That's in there.
here they disassemble it. You can see what's going on in there.
Looks like a UFO. Okay, now next.
Things keep getting bigger and bigger as the slides go on.
Yeah, they got some huge things, and they're so powerful they can lift 50% of their weight by inertial propulsion. Now, of course, SpaceX seems to have done much better than that, or are in the process of doing much better than that. You see, it's hard to design.
Would have both an up and down component, so if it worked at all, it would be kind of a jerky movement.
Yes, pulse power.
Left button down. And even bigger. All right, what's the next slide here?
The lab facility. And then next,
Yeah, next.
they have some kind of a big slab there. A lady at a computer.
Well, they have to test.
I don't know what the black.
They have to test these things. They're spinning at an extremely high velocity. They have to test them on a concrete slab because the thing, you don't know for sure just what's going to happen when you rev one of these things up.
Now we're up to 3D Helmholtz coils.
Yeah, I don't know about that.
There's a person standing there, which indicates how big this is, roughly. Next slide. A sun simulator.
That just looks like a lot of light.
Yeah, all those are little light bulbs. All like.
Here's their test control room. Those were the days of those old-fashioned computers. Test article sensors. Now, what could that be?
I don't know. Next slide. Let's see.
A test article sun sensor.
Well, they have to point the satellites in such a way that they can draw electrical power from the sun, and they have to know where the sun is, so they have to have a sensor.
Yeah, that's another thing that they use for satellite navigation. Was this test article something that was actually sent into space?
Maybe I don't know.
That's what I'm guessing.
You should listen to the talk if you want to know about that, I guess. And as I say, for $30 about, you can get one from Tesla Tech.
Let's see what the next slide is.
DAQ computer. This here reminds me of the digital equipment computers I was using in my neuroscience lab. The old-fashioned ones.
Yeah, certainly that ain't anything you're going to send up into a satellite. So the test article must be ground-based. It's got those little paddles and everything for inputting the individual bits.
What is CMG here?
Control moment gyros.
Control what? Gyros?
Moment. Like moment of inertia.
Oh. Okay.
So there's the test article. It kind of looks like a satellite, but
Well, it's
let's see what the next slide is.
To work at the Boeing lab there, you have to like to build stuff.
yeah. It's an engineer's paradise.
Yeah, you need a good machine shop.
how'd you like to rev one of these babies up and then have it go wrong?
So
It looks like it's on one of those concrete slabs down here.
Yeah, it looks like it's on an
Now, in the data that I presented 2 weeks ago, the gyroscopic activity was not anchored or tethered. In this case, all of their gyroscopic devices appear to be tethered, and of course they'd have to be tethered to the satellite to affect the satellite. That makes sense.
Well, I think what's going on here is that device is basically floating on a pad of air. That's why that's an air pad. So it gives it basically a frictionless surface, so that if that test article is giving a net, center of gravity motion, it'll be able to move across the table, I guess. Right? That would be the trick. If you could get that to just move across the table, then that would be a proof of inertial propulsion. So you could sit there and push that thing around the ground there.
There's no question that it exists, but Boeing came under heavy criticism, I think. I mean, it's not permitted for people to say that Newton's laws are wrong. That's not an optional in academia or really anywhere nowadays.
Okay, next slide.
But in view of what Dennis just said, it's a private company and they're doing stuff in their private premises. I mean, isn't that somewhat isolated from the academia thought control police?
Well, it was until Mike gave his talk. It was until Mike gave his talk. And then it started out with a Boeing number, a Boeing approval number. So they were, and then he retired right after the talk. So they have no one to punish, and it's their own fault because they approved it after a year. So what are they to do? Well, they're now apparently telling people, well, we use inertial propulsion, but it's strictly electromagnetic in nature. And since relativistic electrodynamics does not embrace Newton's third law, there need not be conservation of momentum in an isolated system.
Well, I dare say that even though it's a commercial company and they actually want results, obviously, I'm sure like other companies, they're concerned about the possibility that they will be perceived as being cranks at odds with established views in academia and government. And, even though it's a commercial company, which, as I say, wants to get the correct results, they would make sure that they are not perceived in any way to be at loggerheads with the establishment. I'm sure that's the case.
Yes, that's right. They can even cause trouble for people like Boeing, who is huge. They can they have their ways, and they control the grant money, and they control congressional appropriations, and so you best not fool with them. And so Boeing, who I think has decided that they shouldn't have given Gamble okay, and they're a little miffed because he snuck it by them over a year's period. But he's gone now. He's retired. He's got his pension. So all they can do is damage control and say, no, that's all a mistake. Or at least we don't do that anymore. We're in line today. We use electromagnetic inertial propulsion.
It's a bit like editorial control in a newspaper or something like that, where you have journalists maybe expressing some views, and the top editor maybe is not totally aware of the situation. And he says, no, we have to look at it for other reasons, for political reasons. We can't say that, and we'll have to say it in another form. So it's a sort of an editorial control, I suppose, which is coming from the top layers in the company.
Yes, they don't want any trouble. None.
Plus, they may have defense contracts. Well, not may. They do have defense contracts, which require a certain level of classification of advanced technology.
Yes.
And this whole gamble episode may have created them raised the question of whether they have violated the terms of their defense contracts in terms of keeping technology, certain technology, classified.
Well, you know, they never got a patent on this technology. That's why Mike Gamble, after he waited a year and 1 day after his retirement, now builds small machines like the ones you're seeing and tests them out for Integrity Research Institute, which is run by Dr. Tom Vallone. Gamble and Vallone have teamed up now. And, you know, he has little devices that apparently work with small thrust. What
was the name of that organization you just mentioned, Dennis?
Integrity Research Institute.
Thank you. I'm jotting that down.
Yes.
Okay, getting back to the slideshow. What's the next slide? Second type. And there's a girl there for scale. So is that larger or smaller? Is the test article just the little thing in the middle?
Well, they have various sizes. It's like automobiles. There are little ones and big ones.
All right. Well, next slide then.
Oh, there's our sun panel again.
I guess that's why they needed a sun sensor.
Yeah, they have to know where they are in space, directionally speaking. You know, they have to know just where they're pointing it according to the fixed stars. Or in this case, when they take the sun as being fixed.
Okay, next.
Another one, yeah.
All right, next.
In the talk, Mike explains all these machines and what they're good for and what they're doing and whatnot.
All right, next. Now that definitely looks like some kind of satellite.
Yeah.
Okay, next.
Large gyro.
That looks like a
that's some big one. The biggest one he said that they had.
That you can't even see the person.
Mike said that Mike said that the biggest one they had at the time of the earthquake was actually able to lift 50% of its weight. It had that much thrust. And all this from scissoring. Now, if you had a theory that could predict more than just by cherry picking Newtonian mechanics, you might be able to build one that was extremely powerful.
All right, next.
Rear view of our gyro.
This guy said a gyro's in the back too. All right, next. I mean, that's clearly way more than you would need for orientation purposes.
Yeah. See here, there's two of them. Their axes are not parallel or anti-parallel, I mean. But the theory will still predict what would happen if they knew how to cherry pick it right. Like the quantum mechanical people know how to cherry pick quantum mechanical calculations.
Okay, next.
They were busy little beavers in this earthquake-torn laboratory building.
Yes, Boeing puts up a lot of satellites, and they don't want them to have to burn fuel every time the orbit decays a little bit due to slight traces of atmosphere. So it's financially very rewarding to get this to work.
Very good point, Dennis.
Thank you.
The end. Apparently, this is the earthquake-destroyed building.
Yeah, the building is in ruins, essentially. Part of it's
I'm
still
pretty
standing.
sure the earthquake didn't do that. That's like the demolition team. It wasn't that big an earthquake, I tell you.
Part of it caved in, I think. And the other part, since it wasn't built to withstand an earthquake, the other part wasn't stable anymore. They had to destroy it.
Yeah, I'm sure they did. But it probably just caused some cracks that they couldn't fix. Okay, that was very interesting. So, but the only piece of data we saw in there was that one graph. But certainly they spent a lot of time, money, and effort on this. And it's certainly not just about using gyroscopes to orient yourself, but not change your center of gravity. These guys are definitely trying to change the center of gravity, right?
This address is not, and phone number is not valid. Mike has retired at the end of this talk.
Yep, okay, well, that was very interesting. So, yeah, thanks for sharing that, sending that to James so James can share it with us. Isn't that wonderful? We can go and do things like this just on the fly here on live conferences.
Yeah, it's nice to be able to say something and not have to worry that your job will be over the next day.
Well, that seems to be a problem. Good thing I don't work in physics, right? I'd be fired in a second.
Yeah. Bill had to go to computing after they fired him. Isn't that right, Bill?
That's right. I was at Catholic University, and the Department of Energy and National Science Foundation called the president of the university and said I was to be fired in 24 hours or they would cancel all the 70-some grants or projects at Catholic University, and that was providing the income for a large number of people in physics department, chemistry department, various departments there at Catholic University. So the president called the chairman of the physics department and told him he had to fire me. And the chairman of the physics department called me into his office and told me what was going on. and told me I was officially fired, and unofficially, under the table, they were providing me some income, and they also had given me, they paid for a certain amount of job security, and I got unemployment compensation also. So between the unemployment compensation and the separate compensation of the Catholic University, I was able to live for long enough until I finally got a job at the Smithsonian Science Information Exchange. And so anyway, that's what they do if you don't follow the rules that they have. And the thing I did that got me into trouble was I repeated the arguments of Henri Poincaré in France, showing that both special and general relativity theories are false and could never be true because of the fundamental assumptions that they use to develop the theory do not agree with experiment. And so, and Henri Poincaré developed the certain aspect of natural philosophy, but his was called meta theory. And in meta theory, he proved a certain number of theorems by logic and showed that those theorems indicate which theories in modern science are false, no matter how much or how little data they agree with. And of course, we know, for instance, general theory of relativity cannot predict the gravitational field in our solar system, nor the gravitational force in the outer arms of spiral galaxies. And in order to not have to falsify the theory, they invented another theory called dark matter and dark energy, where 96% of the universe is dark matter and dark energy, and it cannot be observed directly. So if you talk about a fudge factor, 96% compared to 4%, it's 24 times as much dark matter and dark energy as regular matter and regular energy, and that is quite a fudge factor. And in the electrodynamic theory of gravity that I've been working on, you don't need to invent dark matter and dark energy. Your theory of gravity predicts all the gravitational phenomena that we've measured so far, and gravity is decaying, and that explains why the Earth is expanding and why we had a universal flood and we had the long day during the time of Joshua, while the Pacific Ocean was being formed. And it also explains the cosmic background radiation, and you're able to predict the frequency dependence of that radiation, just calculating what comes from hydrogen and helium, which between them comprise 85% of the universe that we know of. You can observe. So there's a little bit of matter out there compared to the amount of hydrogen and helium, and when you see the frequency distribution of the cosmic background radiation, you see where the matter is, because it has a different frequency for the cosmic background radiation than hydrogen and helium. So it's an interesting time we live in. And
so, Bill, good to see you.
Yeah.
So I wanted to pick your brains about something,
Okay.
which is in the mainstream, they show the electromagnetic wave as being a combination of a magnetic and a electric field at right angles. Now, I don't think in reading any of your materials that you ever address that or attack that or agree with that. So I was wondering, what is your stance on that mainstream view that the electromagnetic wave is this magnetic and electric field combination thing?
Well, first of all, at the University of California at Berkeley, a man named William Hooper performed a series of experiments on the properties of the electric fields and magnetic fields. See, it turns out that
Yeah, but I don't want you to go into magnetic or electric fields. I want to go specifically like if you're transmitting a radio wave, what is that? Because I think we know what, a magnetic field comes out of magnet. Electric field comes out of a charged ball.
We showed that the electric and magnetic fields have tensile strength, and that means they are uncuttable. And it also means that all these phenomena have to work together because they're all attached. You understand that? Attached. So if I have energy flowing through the field, a photon or whatever you want to call it, it is attached to all the fields around it, and they're all working together because they're attached. And that is what is not admitted. And also, when the theories of electrodynamics were redone by after Maxwell died, they removed some of the empirical laws and took them out of electrodynamics because those empirical laws predicted some of the results of special and general relativity, but not due to the assumptions of special and general relativity, but due to the empirical laws of electrodynamics. So you've got a lot of things going on here, and the politically correct scientific community is having to go to all kinds of extremes to keep the theories they want in place, instead of admitting they're wrong and accepting the better theories that have been promoted. And so we have to be careful. The people who have worked with me, for instance, to do a new theory of the nucleus, showing the
Well, we don't want to get to atomic. I'm still just trying to pick your brain, because this is kind of typical of, like, I ask you a question and then you go what seemingly seems like a tangent, but really I'm just looking for a yes or no answer. I mean, first of all, are you familiar with the mainstream explanation of how an EM wave is constructed?
They don't have an explanation. They have a problem. There's two kinds of waves. There's transverse waves and there's longitudinal waves of light. And these were discovered during World War II, coming off of radar antennas. According to the politically correct theory of electrodynamics, there is no such thing as a longitudinal wave in the electromagnetic field. But that's not an agreement with the experiment.
So you would be in the camp that the mainstream explanation is just completely wrong.
Yes, and it doesn't use logic. They took the role of logic out of the scientific method. It was in the scientific method for thousands of years before they took it out. And they had political reasons for taking it out. They wanted to be able to promote certain types of theories, and they couldn't if they put logic back in. So they took the role of logic out.
Well, how about this question? Is that when a radio transmitter transmits something, you got the radio station, it's transmitting radio waves, and I receive it on my little clock radio. Did that involve any electric or magnetic fields? And I'm just asking you, okay, how did that happen? How did the signal leap off the transmission tower 30 miles away and then somehow get received by my radio? Something must be going on in between. In your mind, what happened?
Well, energy is being put into the continuous electric and magnetic field that is everywhere in the universe. We can see that, for instance, when we look at what's coming out of the sun and what's coming down on the Earth, we can see those fields very easily. And but we don't see the ones around a radar antenna or a radio antenna so easily. So, but the energy is moving through this continuous, uncuttable electromagnetic field. And so,
well, that's obvious, but do you have an answer, a little bit more detailed answer as to what actually is going on? I mean, is it a wave or is it not a wave? What do you think?
it's a form of energy that's moving the electromagnetic field that is continuous. And it's kind of like if I had a bunch of strings between the radar, the radio antenna and your antenna for your radio that you're listening to. The strings would be vibrating when I transmit, and a certain amount of energy would be received by your radio receiver, and you could turn that into a sound and hear something. And,
okay, well, I can understand. That's not very complicated. This is like having two cans in a string then, right?
yes, well, it's not a string theory per se, but I'm just saying that gives you the idea. You see, we can't see the all of the details of the electromagnetic field very well. The only people that really did experiments to see that were Winston Bostick and Arthur Compton, the Nobel Prize winner for the electron theory. And they showed that the structure of the electron had a lot of information in it. It had both, it was in the shape of a toroidal ring, and it had not only a motion around the circumference of the ring, but it also had spinning around the cross section of the ring. And this produced all the measurable properties of the electron. But what do we use? We use a billiard ball or something like that model of the electron, or a point model, which is what they use in quantum mechanics. Both are false. We know more than that. And so we can't use that type of a model for the electron.
But that's not really getting into, say, radio transmission, because we can transmit radio signal. When you transmit a radio signal, apparently electrons are involved there because we use electricity, but there's no electrons involved during the actual transmission, it would appear, or at least it's not required, right?
Well, we use electricity to produce waves in the uncuttable electromagnetic field. So we have a wave that now goes out, and that wave gets weaker the farther away you go, but that is that transmission. We know how to produce that, and so it's not the electron that's producing it. The electron is helping you disturb the electric field so that you have a pattern, a signal in it that can now be received by a receiver.
Well, I think I liked your analogy with, just being like a string between the transmitter and receiver, because that represents your, tensionable medium of whatever. I mean, it may not actually be a string, but effectively travels on some medium, but it does, but it travels in a very kind of simplistic way, right? Just like there's two cans with a string between it, not this really complicated. It's creating this magnetic field, which is creating this electric field, and then they're self-propagating. I mean, that is the mainstream version of how the radio wave gets from point A to point B. And I've always, I've been having this ongoing argument with Harry about, it's like, well, prove that to me, right? Let's see here. Did my signal just die? Yeah, so. But it just seems that the strangest thing that
Arthur Compton did, he received.
Someone try to talk? I mean, I was just trying to point out to Harry that if the mainstream is going to make this contention about, the electromagnetic wave is this thing that has this time-varying magnetic field in it, then someone should be able to show an experiment showing, oh yeah, okay, there's the varying magnetic field. And
Are you there,
but
Clint?
this is the very thing that no one can demonstrate to me. No one seems to be concerned that no one's actually experimentally shown this to be true, right? It's just bizarre.
That's what Winston Bostic and Arthur Compton did. They did lots of experiments, and they showed that by exciting the electric magnetic field, you can make solitons. And solitons are used to make all the known elementary particles.
Well, that's a completely different topic. I mean, that doesn't have to do with radio waves in particular.
Well, but
I think you have said, Franklin, that even the electric field is not experimentally based. Whereas I say experiments have certainly been done where you can interfere with the magnetic field and the electric field. So, therefore giving some indication that of their presence.
Well, there's no doubt that electric and magnetic fields exist. What's in contention is that when a radio transmitter transmits, that it's using electric and magnetic fields to do that. That's the mainstream contention. What do you think about that, Ian? When a radio transmitter transmits, is it using electric and magnetic fields in the transmission of that wave? That's what mainstream says.
Yes, I mean, my position is probably not terribly different from that, until I have some evidence to the contrary. I have an open mind about longitudinal waves and so on, but I think there does seem to be some experimental basis and theoretical basis to the contention that an electromagnetic wave, which is, the medium for transmission, between a transmitter and a receiver in radio communications, is composed of varying electric and varying magnetic fields. And I do think, until basically I have some contradictory evidence, that they are at right angles to each other, yes, and furthermore, they are in phase. So some of these things that we've discussed before, and there are contrary views for.
Okay, so this is my question to you, is what experiment convinces you of that? Actual experiment.
Of the existence of these fields in the wave, or furthermore, that they are in phase and they are at right angles. What are you asking?
What is an experiment that helps you convince that, or are you merely parroting what you read in textbooks?
Well, I think it's probably a mixture of both. I have to look into the experiments. I'm not quite prepared for it at the moment, but I believe I could do that if you wanted me to do that. Yes,
well,
to a
that's the
certain
very
extent.
point I'm trying to drive through, in that, I've done that. I've tried to look desperately for experiments which confirm this picture and come up empty.
Yeah, but you're fundamentally, I think, questioning the whole basis of an electromagnetic wave, are you? You're saying, I don't see any experiment which indicates that it is composed of varying electric and magnetic fields.
Yes, that's my contention. So I'm just kind of debating that, saying that if you believe that picture, which you think you do, I'm just challenging you to say, okay, well then what experiment that you know about that says, oh yes, they are in phase. I mean, if they are in phase, then you should have been able to see an experiment where you independently measured the magnetic field and the electric field, and you measured their phase, and the experiment shows that, yes, in fact, they are in phase. That would be a very convincing experiment. But
I don't know what level of validation you want. I mean, on the one hand, you seem to be questioning whether they exist or not, whether it isn't another phenomenon, whether it isn't merely electric and magnetic fields. That's on one hand. And on the other hand, you're saying, well, no, I want a very specific experiment to show that they are at right angles and they are in phase. So I'm not quite sure what level of experiment you want.
I want that in phase at right angles experiment.
Okay, well, we'll have to go into a lot more detail, and that might be a project. But
No,
I
we
gave
don't, because
I
I contend it doesn't exist.
Well, you see, the whole
Bob Gray has something to say.
yeah. Just to finish that, the whole system of electrodynamics is basically based on experiment and theory, and I think when you take the two together, you do have some evidence for what you're saying. But anyway, go ahead, Bob.
Okay, Bob, we got John.
Okay, thanks, guys. I would contend that there is no magnetic field. Is there any experiment that shows that the magnetic field exists? And remember, the experiment would have to not include movement of charged particles, because I contend that what we're calling a magnetic field is really the Coulomb field in motion. So it's not a magnetic field, it's the regular old Coulomb field in motion relative to the detector. That's all that it is. It's not a separate magnetic field.
Well, I would still argue that all magnetic fields are in fact due to the motion of charges, but we call that a distinct different field because it works differently from just the static electric field. Now, it may be that the magnetic field
Here's my analogy.
is entirely due to the motional electric field, but the electric field doesn't cause things like compasses to orient to the field line. So
Sure they do, because compasses are made up of charged bodies in motion.
Yeah, but I'm just disagreeing. It's just more a definitional thing.
Yeah,
But
Well, I
you're
don't know.
arguing
If
that
you're talking about
if
something
magnetic
real,
field is defined as electrostatic field plus motion, well, you're saying it's a redundant definition.
that's correct.
Yeah, okay, but that's really a question of semantics.
Well,
it's
no,
quite
if
convenient.
Franklin is looking for an experiment that shows a magnetic field perpendicular to an electric field, and now we're saying the magnetic field is the electric field. So what are you talking about? How can you
Because the magnetic
separate the
field
two?
can be measured separately from the electric field. Like I
No.
can take a
No, it
magnet.
can't.
Yes, you can. I can
You-
take a
because
magnet,
the
and I can
magnetic-
put it in my right hand, and I can take an electric charge, and I can put it in my left hand, and I can measure simultaneously just the regular electric field, and I can also independently measure the magnetic field in the same piece of space. Therefore, they are two different things, right?
No.
Now, they fundamentally still might be caused by charges,
Because the magnet
but we
that you're
can measure
holding,
them in space
the magnet
independently.
the magnet that you're holding is made up of nothing but charged bodies in motion. And therefore
Yeah,
it's
but
the
I can
Coulomb
measure it.
field.
Magnetic
Coulomb
field
field
is
is
a
in
vector
motion.
quantity. Right, Bob?
Well,
magnetic field is a
for
vector
example-
quantity. It has direction and magnitude.
Let me lay this on you. It's kind of an analogy which may not be real good, but think of a tennis ball or a golf ball, whatever sport you like, and that golf ball is moving through the air. It's not spinning, it's not running, and it will move straight, ignoring gravity for the moment. Now, spin that golf ball or tennis ball. It's still moving through the same air, but now it curves. And that is similar to, oh, gee, I have a charged particle and I'm moving it and it's not deflected. But now I'm going to take that same charged particle and put it in a magnetic field and look, it curves. And it's the same kind of thing. No, you're still moving through air. In this case, you're still moving through the Coulomb field, but the Coulomb field is now in motion, or the charge is in motion relative to the Coulomb field, causing it to deflect. And people think that that's something totally separate, totally different. Let's call it a magnetic field. No, it's the same thing. It's just that there's a relative motion going on. And when you have a relative motion, the way the charged body couples to that field is different.
Well, then you could as easily argue that there's no such thing as an electric field, that the magnetic field is fundamental, and an electric field is just a name we give to a magnetic field when there's no relative velocity between the observer and the source. You know, it's a bit definitional, I would think.
But here's another thing. For a magnetic field, pick a point in space and you want to measure the magnetic field in that particular little volume, differential volume of space. Now go into a different reference frame, which has a different velocity, but that velocity is the same as the velocity of the charges creating that magnetic field. What happens to that magnetic field in that volume of space? It disappears. It doesn't exist anymore. You can't measure it, but it's the same piece of space. So is there a real magnetic field existing in that piece of space or not? The answer is both yes and no, depending on the relative motion. So the reality of magnetic fields is only has to do with the relative motion of the charges in motion generating the so-called magnetic field. It's not real. It's just a relative motion thing.
Well, then it's a so-called magnetic field, but it's still something we can measure with our instruments. Call it fictional if you want. I prefer not to.
But then the question of, do you have an electric field and then perpendicular to that a magnetic field? The answer is no. You have an electric field. Period. And then, oh, well, how does the body, a charged body, move through that electric field? Oh, well, it curves in one situation, it doesn't curve in another situation. How do you explain that? The relative motion between what's generating the field and what you're using to test that field. So the question of, well, is there a magnetic field perpendicular to an electric field, to me, doesn't make any sense because there is no magnetic field.
Well, I think that is not correct. I mean, that may be your opinion, but the magnetic field is a thing that magnets create.
And so magnets are created by charged bodies in motion. Oh, wait. I said my 2 cents worth. Go ahead.
I mean, I'm just...
Well, you could make Franklin's question into, prove to me experimentally that there's an electric field and there's an electric field in motion at right angles there too. I mean, the challenge is there, and my answer is that I'm relying also on a theoretical basis, which I know maybe you're a little askance at accepting. You want something, on a tabletop which can actually prove this to you, whereas I can maybe do some basic experiments on the electric and, if I may call it, the magnetic field. And then I can work out Maxwell's equations, and I can find that it does predict these phenomena at right angles and in phase and so on. And then I can find that if I impose any external electric field or any external magnetic field, I can vary the magnitude of these constituents. So to me, that's good enough at the moment. But I think you want a more Lego brick formation, which might not be.
I would contradict the theoretical basis of the EM wave. So, Maxwell's equations gives the relationships between magnetic and electric fields, saying that if you have time-varying electric field, those will create time-varying magnetic field, and vice versa. I mean, that's basically what Maxwell's equations says, and that's perfectly good. That's how our generators work. We take a magnet and we put it around electric charges, and it causes them to move. And we can convert electric charges into magnetic fields and whatnot. So that's the basic. But the thing about that is that the magnetic field has to lag behind the electric field. It's like you have a strong electric field, and then lagging behind that would be the magnetic field it generates.
By the way,
it would not be in phase. This is one of the first problems with that whole thing, which is that Maxwell's equations would indicate that they can't possibly in phase. The magnetic field and electric field cannot rise at the same time.
No, I think that's a slight misunderstanding. I mean, if you would take the basic equations, which are all empirically based, you know, on Faraday's laws, Ampere's law, and Gauss's laws, and so on. If you take those experiments in tandem, and then you look at what they imply, well, they actually imply geometrically or analytically that the two fields are in phase. They must be in phase. It's a bit of a misunderstanding to say they must be out of phase. It's like a quick analysis of them, assuming that there's complete symmetry between the two. It's not as simple as that. I can demonstrate that to you at some other stage if you wish, but that does come out of the curl equations.
Well, I have to say I don't understand it well enough to say that that's right. I mean, that's a possibility. Maybe the equations do say that they need to be, say, in phase, right?
Another point of view is that of Oleg Jefimenko. Jefimenko has written some marvelous textbooks on electrodynamics. And one of his textbooks points out that the notion that a change in electric field will cause a magnetic field, a changing magnetic field, is not correct. The Maxwell's equations are not causal equations. Now, Jefimenko has taken the point of view that charged bodies are causing the electric and magnetic fields, and it would cause an electric field and a magnetic field at the same time, and that propagates together, but a changing magnetic field is not causing the electric field, and vice versa. The changing electric field is not causing the magnetic field. It is the charged body that's generating both.
Change?
Well, in the standard picture of the electromagnetic wave propagating, as you were pointing out, you got an electric vector pointing one way, magnetic vector 90 degrees to that, and as the electric field is changing, the magnetic field is changing, and people tend to say that the changing electric field is causing the changing magnetic field. And Jefimenko, doing the theory, doing the math, is pointing out that that's an incorrect interpretation of Maxwell's equations. Maxwell's equations are not causal. Now, with all due respect to Bill Lucas, who would say that, well, the charged bodies are not causing the fields, it's the fields that it's causing the charged bodies, that would be an interesting point of view, too, to discuss.
Also, we're ignoring the experiments that were done by William Cooper at University of California at Berkeley. He measured 13 properties of 3 types of electric fields: the static field, the velocity-dependent field, and the time-dependent electric field. He also measured 13 properties of the magnetic field: the static magnetic field, the velocity-dependent magnetic field, and the time-dependent magnetic field. And they are different. The properties are different. Some types of fields cannot be shielded, others can. And you can't explain that with the type of approach that we've been taking here, because we're ignoring the fundamental experiments. These experiments are more fundamental than the ones behind Maxwell's equations.
I generally agree with what you're saying, except for I can't find enough detail on every single point there, on every single experiment. What exactly are the properties that were measured? What was the result, numeric result, and what was the theoretical development to confirm it, etc. I have Bill Hooper's book, one of his books, and it to me it describes it kind of generally. It does give some detail, but for me, there's just not enough to really dive in and understand exactly every property that he was measuring and what exactly the results were.
Do you have the book that gives each of the experiments he performed and how he performed them, and pictures of the apparatus and all that kind of stuff?
Well, that's what I'm kind of getting at, is I don't think I do. I think I have another general write-up of Bill
I'll
Hooper's.
send you the name of the book, and if I have a digital form of it, I'll send you a copy.
Oh, that'd be fantastic. Thanks so much, Bill.
Sure.
I think Alistair had some comments here. So Alistair, I put you in the live room here. If you have any comments.
I was wondering what disqualifies the magnet as a tool of detection of an electromagnetic field. Or is
Are
it?
you using a wave, like a radio wave, using a magnet to detect an electro?
Sorry, did I say, I might have said magnet, I meant compass.
A compass.
Yes, a compass, a simple compass. It detects the Earth's magnetic field, does it not?
I would say it does.
And what are we looking for again? An electromagnetic field?
We're looking for electromagnetic field. So if you were to take a compass and put it in the path of an electromagnetic wave, according to the picture given by Mainstream, you would see it point, say, north, and then as it switched around, you'd see it point south, and then you'd see it point north as it switched directions, is what you should observe, right?
Oh, I see what you're saying and what you're looking for.
And so I should be able to put whenever if I had a super sensitive small compass, anytime I ran a radio transmitter, I should see that compass needle move around because it's going to be living inside of a time varying sinusoidal thing, and they show the vectors, moving in opposite directions, get bigger and then smaller, and then moves to the opposite side, gets bigger, smaller. This is what we should observe happening in the electromagnetic field as it travels, right? And you can see it would be north-south, aligned like that, right? It's
Yeah, I can see that a compass isn't what you were looking for. I was a little muddy. I do have a question. Is the electromagnetic field the same as a four-dimensional field?
I don't know. I don't know what a four-dimensional field is. I don't think they exist.
Well, I thought existence was supposed to be four-dimensional with time as the fourth dimension, which basically means that wherever there's a cube, there's a second cube, because that's the fourth dimension, kind of doubling up on the density of existence.
What I like to think of when they say 4 dimensions, I don't think that it's appropriate for the Einstein point of view to, or whoever point of view it was, to take time as a dimension, because I can't move backwards in time. I can't move forward. I can't change that. So I look at it more as a parameter. There are 3 spatial parameters and a time parameter, and for some reason, physics seems to want to call that a 4-dimensional space.
I absolutely don't agree with the application of the word time to a dimension either. I was just using it as a mathematical example of what we call 4-dimensional and asking if the mathematics of that was the same between a 4-dimensional space-time and a 4-dimensional electromagnetic field.
Well, if you're looking at waves,
Well, if I may jump in here, Alistair, they don't put time as the fourth dimension. They multiply the speed of light, which is a distance divided by a time, times time. In other words, you see CT in the so-called 4 vector. Okay, so time is actually not put in, mathematically speaking, in a precise way. What they're doing is using a proxy for time, which is how far light would travel in that amount of time. End of story. I just wanted to make that comment. So when we say that there's a 4 vector with time in there, time is not in there. They've converted
a very similar point to what I was about to make. Although what I was going to say is that if you're looking at the wave properties of phenomena. If you put in instead of as you know, you put x1 is x, x2 is y, x3 is z, x4 is ICT, which is, you know, the imaginary number square root of -1 times the speed of light times t. Well, if you put that in as a fourth dimension and do the mathematics, you know, you get the four-dimensional D'Alembertian wave equation. So in that sense, it can be considered mathematically as a dimension, but it's just again a definition.
Gotcha. Hey, Bob Gray. Oh, he's muted.
No,
Anyway,
that's all right. Go ahead.
As an alternate to calling time a dimension, I do see that mathematically there's like this second half to existence, but I don't like the use of time. I prefer tempo, but I don't think of it as a spatial dimension. It's just a property of a given point of existence is its tempo. And
That's
then
interesting.
and then that way it gets rid of this whole can you move backwards and forwards in time crap and time going both directions and all that other kind of crap, because every point has a tempo is different than every point having time and all that.
That's interesting.
A bunch of stuff.
Yeah. Nice.
You're welcome. Alistair out.
All right. So getting back to we were talking about here. So I'm kind of arguing against that the radio wave actually has anything to do with the magnetic field. For example, you know, I'm looking for the experiment that would show the compass needle moving from one side and then flipping around to the other as this thing moves around. Now, we just actually don't observe that. I'm more of the feeling that it's just like the cans between a string kind of deal. But that's a very simple kind of idea, that the radio transmitter is like the can on one end, and then there's something between the transmitter receiver, like a string, whatever it is, and it terminates in another similar can. And that particular picture, you know, obviously doesn't involve any magnetic or electric fields. It's just a straight longitudinal wave through a string, right? So while I can't prove that, you know, that's kind of where I'm headed. Now,
well,
typically,
I would maintain that it does involve the analogies of the electric and magnetic field, as we know. We've discussed this many times before, because the density of the string would be analogous to the magnetic field, and the elasticity of the string would be analogous to the electric field, and the two combined give you this sort of vibrational energy transmitted from one can to the other. So I could put the question back to you. I mean, you're accusing me to a certain extent, you know, fairly, of maybe just accepting the mainstream interpretation. But I could put to you, I mean, why do you really not want to accept it? And what is your alternative explanation?
Well, the reason why
the wave is.
The reason why I do not want to accept it is because, from my own personal bias, you know, I'm an etherist. And I know that kind of transmission simply is not possible in my medium. So that's one reason why I am against that kind of transmission, because that can't even be represented in my medium by how I figure out how magnetic and electric fields are actually what they actually are. Because if you understand that the magnetic field is actually, it's a polarization of my dipole particles, right? So if you've got a whole bunch of those aligned, that is the magnetic field. So if you know that, then you know that that cannot possibly be swapping positions, right? And you know that the only way a magnetic field can be generated is in the presence of a moving basically must be in a circular path kind of thing by a moving electric charge, and that the magnetic field cannot be generated in the absence of an actual moving charge. So another reason why I object to that picture is that this thing cannot be self-propagating, because there are no moving charges in, like, you know, blank space between the transmitter and receiver to create a magnetic field, right? So that whole idea dies just right off the bat there. And, you know, and Maxwell's equations are all expressing these things in terms of real charges, right? That are present. I mean, you can physically identify them, right? It's not like, and then they're just taking it totally out of context, sticking it into blank space where there aren't any charges and aren't any magnets, there aren't anything to generate or propagate these fields physically, and they're just like adding apples plus oranges to get grapes. It just seems a complete mistake.
But surely, with respect, that's a bias, you know, and perhaps you've come upon it the wrong way. You've decided what, I'm an etherist as well, by the way, and yet we disagree on this matter, but you've decided what the ether is composed of, and you're finding that this explanation doesn't fit in with your formulation, and therefore you're looking for reasons to see why it's wrong. So
yeah, so that's one motivation I give to you.
Well, thank you for being honest, but I think you might be coming upon it from the wrong angle, or let's say you should at least dismiss from your mind for a period of time your own conception of the ether, and maybe look at you know, the EM phenomenon, and then maybe
that's why I gave you the other reasons that, you know, Maxwell's equations require actual charges, actual magnets, and in the middle of space, none of that stuff exists. So no matter what you believe, you just can't take Maxwell's equations and then put them in this completely blank area that has got no charges and think that they apply, because they don't. I mean, the Maxwell's equations applies in the realm of actual charges and actual magnets to create actual magnetic fields from actual charges, not something happening out in the middle of nowhere in complete vacuum space, right?
Yeah, I think that's an argument against Maxwell's equations applying in vacuum space, you know, which is what modern physics says. But I don't think it's an argument against Maxwell's equations applying in a sort of the medium of free space, which has analogous dielectric and magnetic properties, as Maxwell himself would have, you know, postulated. And I think you agree, because we both agree on the properties of the ether. You know, they're experimental, but it's the interpretation which actually I think differs.
Well, that's possible. Like, once again, it could be one way or the other. But those are my reasons why I don't believe that needs to happen. I mean, but mostly I don't like it because there's no direct experimental proof, and there should be, right? If someone showed me the experiment showing that, yeah, I put a sensitive squid magnetometer in front of this radio antenna, and I saw that it was switching directions and magnitude, as shown in those nice, neat little pictures in the textbooks. And I say, okay, cool, got that. But no one has ever been able to show me any such experiment. I mean, that's the kind of the basic experiment. All we have is like this indirect evidence. You know, most people say, oh, polarization, that means it must be transverse wave. It's like, no, polarization is not any kind of direct proof that whatever's creating that polarization is like a transverse wave. I mean, some people literally think that there is something moving up and down like an earthquake wave, and that is not true. Even from mainstream is just saying that there's a electric field, it's gaining in magnitude and then decreasing, because the electric field is a vector quantity. So it's just a direction and a magnitude, you know, just like my finger. So my finger gets bigger, finger gets smaller. There's nothing actually moving up and down, right? Not like a rope on a going through a picket fence is nothing like that, even in the mainstream conception of the electric field. It's supposed to be literally rising electric field, rising magnetic field, and then decreasing electric and magnetic. It's supposed to go like that. It's just two fields that are increasing and decreasing. That's what the true picture is saying. And I'm saying that that's a bunch of baloney, that the transmission is much more analogous to, say, sound waves, which is something that I can't understand. So I'm trying to get the explanation for how this transmission works to be like sound waves. And that's why I kind of like, the can between two strings explanation, because that is just a sound wave, actually, really. I mean, it's going through the string instead of the air, but fundamentally it's the same thing. It's just a back and forth motion. You just have some matter in between, and it's just literally pushing it, shoving it directly, back and forth to create the oscillation. And that's what we recover back as your original voice. So that's what I'm kind of pushing. I'm saying that whole picture of electric magnetic field, it's baloney, because no one's actually been able to show an experiment showing that, right? And you should be able to do that. I think that's well within our experimental ability to do that. Maybe when they first invented this theory, no one could come up with a magnetic sensor that was that sensitive, but certainly they do exist now. So there's really no excuse why they shouldn't do that. But right now, everyone just seems to accept that as, kind of the gospel, and it may be wrong.
As we know, I too am an etherist, a purely physical, mechanical, no magic etherist. However, I don't dispute or disagree with the existence of forces or fields. However, I suggest they are emergent. So you can be an etherist and still wish to entertain and accept that an electromagnetic field exists. It's just that what causes it. So it's not magical. It's just the motion of the underlying particulates causing the impression of, or the creation of, the four-dimensional electromagnetic or Coulomb field.
Well, I think we need to separate two things here, because we have, say, the electric field, which is a thing that comes out of, say, a charged ball. But then we have the electromagnetic wave. So I think the electromagnetic wave is what is in contention here. Like, what is that thing?
Well, I'm not. I'm not trying to reinforce one position or the other. I'm just mentioning that being an etherist does not exclude accepting the existence of an electromagnetic field as a emergent phenomenon versus a fundamental field. So that you can't just say, oh, etherists can't believe in the EM field. No, that's not okay. I don't agree with that. I was just saying, don't make that lump statement, and understand that you can accept the existence of something without necessarily agreeing that it is fundamental.
Well, I would agree with all that. It's like, yeah, as an etherist, though, I think you have to be able to explain the physicality of the observed field. So if you have a charged ball and you see it, attracting other charged balls or repelling other charged balls, or I stick a meter up to it and it gets bigger and smaller, you have to be able to explain what those are. I mean, I think that would be the first thing an etherist theory would have to explain, is how that works. I mean, you can't deny that, like, an electric field exists. I don't think that you could ever deny that.
That was my point. Within mainstream physics, there are some established phenomenon that it makes no sense to disagree with. You flick a switch, the light bulb turns on. It would be ridiculous to disagree that the light bulb turned on. But the existence of a phenomenon, you still have the question of, is it a fundamental phenomenon or is it an emergent phenomenon? And I just wanted to make sure that we didn't forget that, because if we forget that, we can be saying the exact same thing and yet arguing with each other.
Yeah, that happens frequently, but I think it's an important distinction you're making there between a fundamental, something which is fundamental versus something which is emergent.
Absolutely.
So, I mean, the electric field could be fundamental. I mean, it just could be something that just happens.
Yeah, if you believe in magic.
You know, it just, you have a positive charge and it repels other positive charges, and that could just simply be fundamental. That's just what it does. Or it could be emergent.
Yeah.
In the sense that, you know, I say it's emergent because the positive charge thing is emitting something, and it's emitting the same, and the other positive charge is emitting something through the medium, and something is causing, when those two things interact, to cause the particles to move away from each other, right? That's an emergent
exactly. And when you
thing.
start to understand emergence, then you can stop believing in things like forces and leave those for Hollywood and Star Wars and get back to doing real physics.
Well, that's what I try and do. I mean, in particular, you know, I think it's actually a wave that's coming off of the charged particle, right? And the wave is pretty easy to understand. It's just like any other wave. But when the wave interacts with the same wave of the same type, that causes pressure to build up between them, and that causes them to get shoved apart. Now, basically, the thing that's causing the force is actually collisions, just Newtonian collisions, right? Particle A hits particle B, causes it to go that way. So I don't think that we would consider that. That's not like force at a distance, which is what you're trying to explain here.
And
you've got particle A, particle B, they're both have the same charge. What is the mechanism that causes them to go apart? You know, I'm saying that literally there's more particles hitting them apart than are hitting them going together. Is what I'm trying to motivate there.
It sounds like your ether simplifies down into being 4 dimensions with every point pushing outwards and every point attracting inwards, which is almost the same as somebody else talks about tensors, with every point is like an elastic that can be stretched or contracted. It sounds like everybody sees the same math, and it all translates down to this 4-dimensional dual density space. Seems like we all see the same thing, we just approach it different ways. Sometimes it seems that way to me. Maybe people would disagree.
Well, I don't know about this 4-dimensional thing. I mean, what's the fourth dimension?
I just mean a way of saying that there's 2 halves. So any given point has an A and a B. There's this like bipolarity or split, call it what you will, that any given point in space has 2 aspects to it, not one aspect to it. Gives you the 4th dimension.
Yeah, still not sure I quite understand what you're saying there.
Okay. But
I think, you know, what the important things you bring up are that, you know, as etherists, that the forces certainly do exist, just like, you know, the light bulb turns on. We can't deny that. And that we can either think of it as fundamental, as just being there, in which case it doesn't need an explanation, or it being emergent. And so I prefer it to be an emergent out of a generally chaotic system, right? Just a system of just like gas in the room here, right? Not terribly ordered or anything like that.
A lot of gas in the room there, is there, Franklin?
Pardon?
There's a lot of gas in the room there, is there, Franklin?
There's a lot of gas here, yes.
It was just an odd phrase, that's all. Sorry. Pardon my odd sense of humor.
Right.
There's hot air as well.
A lot of hot air, yes. That's a lot of hot atmosphere here as well. But that's why I kind of started this discussion about something which is, mainstream accepted extremely well. Ian believes it, right? Ian believes that all that stuff about electromagnetic waves. And now I will admit that some things are very hard to explain, like circular polarization. Okay, you got me on that one. I'm still trying to work on what in the heck that is, because that is used extensively in satellite communications, and it's easy to explain some polarization effects. Thinking now of this bit about transmitters coming from can to can on a string. Well, once you have a string, then that has a particular vector direction, and that can be polarized, right? It didn't need to have anything moving up and down in order to, say, polarize the direction of my string, because then that's just, once again, the rope through the picket fence, right? That I can get it to polarize so that only the direction heading in the vertical direction gets through, and if I put the string the other way, then it's not going to get through. So, that's...
Or more generally, Franklin, elliptical polarization, where the contributions from the electric and magnetic fields are not equal. So, that's another thing you have to explain, I suppose.
Yes, I think that if there is an actual answer to something that actually relies upon the electric and magnetic field, it would have to be something like that, right? That if there's something that actually totally relied upon, say, the magnetic component versus the electric component. Since in my view, the only thing that can truly exist would be just a wave front and a compression type wave. So once again, that's my bias, because it's like in my realization of how space works, it's just a randomized gas. It's nothing that more complicated than that. So it's completely incapable of doing that. So, it's my burden of proof to show, what do you call that? Elliptical
polarization. Circular polarization is a particular example of elliptical polarization, where the contributions are equal. Elliptical polarization is the more general circular type of polarization, if you like.
Yeah, because near as I can tell, there's actually nothing circular about circular polarization, but I'm still trying to figure that one out. But they call it that, and they can draw beautiful pictures of showing these corkscrew things going on, and those are right, quite analogous to the standard, just non-polarized wave kind of thing. But I still think that is does not making any sense. But I'll admit that that whole circular polarization thing, I don't have an answer for. Other than I still don't like it. How about that? So.
Well, it's no harm in asking the questions. It's prompting a lot of investigation and discussion, which is useful.
I should just ask somebody who's expert in this field. So show me that experiment that shows the north-south pole changing. I mean, that should be child's play now, right?
I think maybe some of the scattering experiments, which I've probably referred to before, things like splitting of spectral lines in magnetic fields and electric fields and measurements thereof. I think they may be useful to look up.
Well, once again, the region of applicability would be completely different as far as spectra and radio wave propagation, I would say, are not at all related, I would think.
Yeah, your question extends to light as well. Light being an electromagnetic radiation, being an example of electromagnetic radiation, whose properties presumably would be subject to electric interference and magnetic interference if the sort of general mainstream explanation, which I generally adhere to, is correct.
Yeah, we got radio, we got light, we got microwaves, we think infrared. We think all these things are the same thing, just different frequencies. So I'm probably cool with that. But I just wanted to put that doubt in everyone's mind, I guess. So, but it looks like we've come to the end of our 2 hours. Always fun chatting with you guys. Thanks for everyone participating today. So to summarize, we were discussing the new paper that Dennis Allen had put out, and you can get that on ResearchGate, and you can also get it on Amazon. And we got the presentation from Dennis about the Boeing slides about how they built these gigantic experimental setups to do this inertial propulsion. And it's, quite convincing that, yeah, they were definitely trying to move the center of gravity with these giant devices here and satellites. So definitely there is something to it. And it's just not clear whether they actually implemented that in actual satellites and just calling it, electromagnetic propulsion or something. But definitely something was going on there. And then the second half of our discussion centered around, what do we really believe about electromagnetic waves? For me, I think it's a gigantic misnomer that they call it the EM, electric magnetic wave, because I don't think that anyone's ever shown me that there is anything electric or anything magnetic actually going on between point A and point B of a transmitter and receiver. And we talked a little about Bill, who he kind of also disagrees with that picture that there's just a medium, and maybe the analogy of a string between two cans is more appropriate for what's going on, and that there's just a disturbance happening on the transmitter. That disturbance travels somehow across space, and that disturbance impacts the receiver in a similar way, and that's how we get radio waves, right? Okay, so that will summarize for today, and we'll see you next week then. All right, bye-bye.